And we just write this dot x when we put variables just to remind us what type they have. Okay. So yeah, this is another sort of notation for this big yellow arrow here. And we see that it sort of makes sense, like this set of x1 that's in relation with x2. Or, you know, is it true that x2 is one of these things that belongs to this? Well, it doesn't really belong to that set, but it's true that it's like one of these things that makes x1 satisfy this phi relation with respect to x2 and so on. So okay, finally then, what we want to do is get some experience using using this for all x kind of term. Okay. So this is a formula. It's a term of type omega, and no, actually, it's not. It's not a term. It's an arrow. It's just an arrow. It's just an arrow in regular topos theory. It's an arrow from omega to the power of x to omega, and it's defined to be the classifying arrow of the name of tx. Okay, so tx is the truth arrow after the unique arrow from the terminal objects to, sorry, tx is the true arrow after the arrow from x to the terminal object, and the name of tx, which is, we put tx in quotes, what we really mean is the transpose of tx after the second projection. Okay, so we think of this kind of arrow 1 times x, for example, and then if we do P2 on that, we get x, and then doing tx on it, we do exclamation mark x to get to 1, and then we get true, and this is called tx. Okay, so if we take the transpose of all of this, then we get an arrow from 1 to omega to the power of x. Sorry, this goes to omega, not true. There we are. Yeah, we get an arrow from 1 to omega to the power of x, and we call that the name of tx. Okay. So for all x is defined as the classifying arrow of the name of tx. And so we're going to try and understand what this term here means. Okay. So again, this is a formula, and it says for all x1 in x, for all x1, we have phi. So how can we interpret this? Well, this is actually just shorthand for all x, for set of x1 dot x, such that phi and we know that for all x is just the classifying arrow of the name of t. But anyway, what we're writing with these square brackets here is we're actually interested in the extension of this. So we want the sub-object, which is like classified by the interpretation of this term here. So this general t element of x, v here, is going to be in this sub-object corresponding to this extension, if and only if, when we interpret this term and operate it on v, we get true. I put t subscript t, I mean like the truth arrow after the arrow from t to the terminal object, okay? Anyway, we know that this here is this stuff here. We know that for all x is just shorthand for classifying arrow of name of tx, and we know that this set builder notation is just it's just this notation here, this lambda notation, which just means transpose. So we can write that this is true if and only if doing the classifying arrow of t of x on transpose of interpretation of phi after v gives true. So okay, what that means, if we go back, think we want to sort of go from talking about this classifying arrow to talking about the actual monic that it classifies. So we can say that this is true if and only if transpose of interpretation of phi after v is in the name of true, which is happening if and only if transpose of interpretation of phi after v is name of true after arrow from t to terminal object. And this really means tx after p2 all transposed after arrow to terminal object. Now if we transpose both sides of this equation, we get this equation here that says that interpretation of phi after v times 1x is equal to true, okay? Now let's write this with the v times 1x. We'll just expand that out so we get that interpretation of phi after v p1 comma p2 is true. And notice up here that this stuff here is just interpretation of phi, and we've already shown up here that interpretation of phi after something is true if and only if the two components of that thing are equal. So this happens if and only if f v p1 equals f p2. Now how do we interpret this? Well, when t is the terminal object, this projection here doesn't really matter. We can just think of it sort of producing this v out of nowhere. And so this v would be like a constant or a point, and then we'd be saying, well, for any x we put in here, we'd always have that f of v equals f of x. Okay, so if you think about now, we can do the sort of magic bit. So what's this mean? Well, it sort of means, just using this notation, that v is such that for all x1 of type x, we have that fx1 equals f of v. I'm getting this just from looking up here and thinking, well, we've got an x1 there and our phi is just this. So our shorthand notation is giving us exactly what we what we'd expect to see in set theory, but this is all happening in general topos theory. Pretty interesting stuff, I think.